Hey guys, in this video we're going to talk about Chapter 14, Section 6, the chain rule for multivariable functions. Okay, so in Calc 1 we talked about the chain rule for single variables, so if we had one independent variable. Now in Calc 3 we're going to have multiple independent variables, and so we need to expand our definition of the chain rule up to another dimension, okay? So this is how we did it. First of all, we had this composite function, so we had a function g of x as an input for f, and the way that we did the chain rule was we took the derivative of the outside function, leaving g in there while we did it, and then we multiplied by the derivative of the inside function. So, for example, if we have the function y equals 2x plus 3 squared, and I want to take the derivative of y with respect to x, what we can do is we can make a little substitution, right? So we can say, well, let's let u equal 2x plus 3, okay? And what we can do is we can say, okay, well, if u is equal to 2x plus 3, then y is equal to 2x plus 3 squared, so y is equal to u squared. And so the idea here is, we're going to take the derivative of the outer function, right? So the derivative of y with respect to u is going to be this. It's going to be dy du, and that's going to be equal to 2u, okay? In a similar way, we can take the derivative of u with respect to x. So this is the derivative of the inner function. So when we take that derivative, we're taking the derivative of u with respect to x, and that's just going to be 2 using the power rule. Okay, and so what did we do with those two derivatives? Well, we just multiplied them together, right? We have the derivative of the outer function times the derivative of the inner function. So we got that the derivative of y with respect to x using the chain rule was equal to the derivative of the outer function dy du times the derivative of the inner function du dx. And we wanted everything in terms of x's and y's at the end, so we can sub our u back in. That's in terms of x. Okay, so we get dy du is equal to dy du, which is 2u, but it's also 2 times 2x plus 3. Times du dx, which is 2. And then we can, simplify this if we want, but dy du is equal to 4 times 2x plus 3. So what's the purpose of the chain rule? Well, the purpose of the chain rule is if you're trying to differentiate a function y with respect to x, we came up with a way to link x and y together through intermediate derivatives, right? We said, well, u is a new function in terms of x, and u is equal to 2x plus 3. Well, I can write y in terms of u as well. So basically, we're linking x and y with a new variable u. We're chaining them together, and that's how the chain rule worked. Notice that, one thing we can think about here with this chain rule is that on the diagonals, these u's, quote unquote, cancel out, and so we're just left with dy dx. Okay, so let's look at a sketch of the proof of the chain rule when we have a function of two variables and both of those variables depend on a third variable. Okay, so what do we have here? We have a function z equals f of xy, so we can say that z is the dependent variable and x and y are the independent variables. So z depends on x and y. Okay, and we also are given that x is equal to g of t. So x is a function of t. That means x depends on t. So x depends on t, and so does y, right? Y is a function of t as well. So x and y depend on this third variable, on t. So ultimately, what does z depend on? So ultimately, z, because z depends on x and y, and both x and y depend on t, z ultimately depends on t. Okay. All right, so knowing that fact, we want to think about, to sketch this proof, we want to think about what the change in z is, right? Because what we're trying to figure out is what is dz dt, the derivative of z with respect to t, and somehow we need to chain all of these variables together to get that relationship. So what we're going to consider first is we're going to consider the change in z, what that equals to. Well, z depends on x, right? And y, which ultimately depend on t. So the change in z is going to be the amount that x changes z plus the amount that y changes z, right? Because again, z depends on x and y, and we're going to bring in the t in just a little bit. Okay, so let's consider the amount that x changes z, okay? So we can think of this in terms of slope, right? We know that the slope in the x direction, when we're talking about z as our independent variable, well, that's going to be the change in z, or maybe I can write it like this, the change in z over the change in x, right? And so the amount that x changes z, if we multiply both sides by the change in x, we have that the amount that x changes z, the change in z, is going to be equal to the slope in the x direction times a change in x. All right, so let's write that down. So we have this is equal to the slope in the x direction times a change in x. Right, that's what this was. And in a similar way, we can, use the same idea with y. The slope in the y direction is the change with z being our dependent variable. It's going to be the change in z over the change in y, and therefore the change in z with respect to y is the slope in the y direction times delta y. Okay? So let's go ahead and write that out right here. So slope in the y direction times delta y. Okay, so this is the change in z. Well, what are these m's? What do those mean? What does this mean? What does this mean? Well, this is the partial derivative with respect to x of z, okay? So one way we can denote this is with our partial derivative fraction. That's partial of z with respect to x. So that's just the slope is in the x direction is the partial derivative of z with respect to x times delta x equals delta z plus, and in a similar way, the slope in the y direction is just going to be the partial derivative of z with respect to y. So that's partial z with respect to y times delta y. Okay? All right, so again, if you're not completely following this, you can think about it a little bit longer. It's not imperative to know this outline of the proof to complete your homework, but just to give you an idea of where this formula is coming from, okay? Okay, so now we have this. Now what I'm going to do is I'm going to divide both sides by the change in t, Okay, I'm going to divide both sides by the change in t. And what I'm going to do at this point is I'm going to take the limit as delta t goes to 0 of both sides. Now the partial derivative, I don't have to take the limit as delta t goes to 0 because I don't have a delta t explicitly written there. But I am going to take the limit as delta x over delta t goes to 0. Okay. All right, so what is this value right here on the left side? If I take the limit as delta t goes to 0 of delta z over delta x, well, again, this is slope. This is something that we talked about in Calc 1. We have the change in z over the change in t, and so if we're making the change in t super, super small, remember what we're doing here really is we're taking slopes. Okay, so we're taking slopes where z is our height and t is our width. And what we're doing when we're making t really, really close to 0, we're making these points get super, super close to each other, right? And that's going to produce the slope of the tangent line rather than the slope of the secant line, aka the derivative, right? So this, when delta t goes to 0, this is actually going to become the derivative of z with respect to t, right? That's that whole limiting process is about. Take the limit as the secant line becomes the tangent line, right? As the 2 points get really, really close to each other, take the limit and you're going to get the derivative, okay? So in a similar way, this guy is going to be the derivative of x with respect to t plus partial of z with respect to y, and then this guy is going to be the derivative of y with respect to t. So this is our chain rule. This is our chain rule when we have a function of two variables, x and y, and then those x's and y's depend on a variable t. Okay, so this is the chain rule. So I'm gonna explain what this means, abuse of notation. So what I just showed you on the previous slide is the following. I said dz dt is equal to partial of z with respect to x times dx dt plus partial of z with respect to y dy dt. Now, in this video, I am going to be sloppy and I am going to not write the partial derivative symbol. I'm going to, instead of writing this symbol, I'm going to write d. So I'm going to write it like this for you guys to get intuition. Just know that this is secretly the partial derivative of z with respect to x. What's the difference, right? What's the difference between this guy and this guy? Or, a partial derivative and a regular derivative with the regular d. Well, the partial, you're going to have more than one variable in the equation. The regular one, we only have x as a function of t. We don't have x as a function of t and something else. That's why the d is written normally like that. But the reason I'm going to write the partial derivative like this, even though it's technically not correct, because we have a function of multiple variables, it doesn't really make sense to say what's the derivative of z with respect to x without indicating that there's more than one variable there. But the reason I'm doing this is to give you some kind of intuition and why the chain rule, how to set it up basically to do the mechanics for these problems. So this, I'm going to say this is dz dx plus, and then for the other partial, again, this is in quotes, instead of the partial of z with respect to y, I'm going to write it like this. I'm going to say, instead of that symbol right here, we're going to write dz dy. Okay, and the reason is because you can see what things look to, so you're going to see what looks to be cancellation, and it's going to give you some intuition of how to set up the problem. So for example, dz dt, you can see with these x terms right here that along the diagonal, if those quote-unquote cancel out, you see the dz dt right here. You see it right there, okay? And same thing over here. If these cancel, you can see the dz dt. So even though this notation isn't technically correct, it is going to help you when you go about solving more general chain rule problems. Okay, so we have z as a function of x and y. Z equals x squared plus y squared. X and y are both functions of t. So x equals 3t, y equals t squared minus 4. So the question is, what is dz dt? And we have this formula that relates all of our variables, so we have the chain rule that we're going to employ here. Now, from here on out, I'm going to treat the partial derivative with respect to x of z. I'm gonna act like this is dz dx, even though I know that it's not really. That's what I'm going to do to make our computations make a little bit more sense. And then the partial with respect to y, I'm going to call that dz dy, okay? Alright, so with that, we have dz dt is equal to dz dx, dx dt, plus dz dy, dy dt. And we can sort of see that even though these really aren't going to cancel, we can think of them as canceling just to get some intuition behind what's going on. We get dz dt is equal to, basically 2 dz dt. So that's just an intuitive way of thinking about it. It's not really equal to 2 dz dt because dz dx is actually the partial derivative of z with respect to x, but that's just how you can get some intuition behind what's going on here. So we need all of these variables to compute dz dt. So the first thing we can do is we can compute the partial derivative of z with respect to x, right? And so we have z here, and so if we treat y like it's a constant, the partial derivative of z with respect to x is just 2x. The partial derivative of z with respect to y is going to be 2y. And then, so we have this taken care of. We have this taken care of. Now what about dx dt? Okay, so this is the derivative of x with respect to t. So looking at this equation, if we take the derivative of both sides, we get dx dt is equal to 3. All right? We're just taking the derivative of the function with respect to t, the function x with respect to t, and we get 3. So that's 3. In a similar way, dy dt, so we're taking the derivative of y with respect to t, so taking the derivative of both sides, dy dt is equal to 2t. Okay? Alright, so putting that all together, we can get what we were trying to get to begin with, which was dz dt. So that's dz dx, which is 2x, times dx dt, which is 3, plus dz dy, which is 2y, times dy dt, which is 2t. And we want our final answer in terms of t, right? Because we're trying to find the change in z with respect to t. So we want our final answer to be in terms of t. So we go back up here and we see, well, we know that x is 3t and y is t squared minus 4. So let's write that over here. So x is 3t and y is, what was it, t squared minus 4. So we can just sub in those values so that we make sure that we're in terms of t. Okay, so we have dz dt is equal to 2 times 3t times 3 times 2 times t squared minus 4 times 2t. And you can simplify if you want to, but you can just leave it like that. That is perfectly fine. So that is dz dt, the derivative of z with respect to t, and we found that using the chain rule. Okay, so here is the chain rule again. Alright, so here's another example. Suppose we have a function z. Let's see, get my notes right here. Yeah. Okay, so let's say we have a function z with independent variables x and y, and it's defined to be x sine of y. Let me write that little y tail longer. We have x is equal to t squared, so x depends on t, and y also depends on t. Y is equal to 2t plus 1. And so we're going to say that z is a function of t, right? Because since z is a function of x and y are functions of t, ultimately z is a function of t. And we can figure out what dz dt is, or g prime of t, by using the chain rule. Alright, so let's go ahead and do that. So we're trying to find dz dt, or g prime of t, right? If we take the derivative of z with respect to t. Alright, so I like to just list out, what I can find, basically. So I look at my first function z, and I'm looking at it, I'm saying, okay, well, I have z, so I can find the partial derivative of z with respect to x, even though I'm not using the partial derivative symbol, that's what I mean here. I can also find the partial derivative of z with respect to y, and that's what I can find with z. Now x, I can find the derivative of x with respect to t, okay? And then I look at y and I say, oh, well, I can find the derivative of y with respect to t as well. And once I have all of these values, I can just sub them into my formula right here, keeping in mind that this partial with respect to x is this, and the partial with respect to y I'm calling this, even though it's not technically correct. That's how I'm thinking of it here. Okay. Alright, so dz dx, so the derivative of z with respect to x, I have to use a chain rule. So keep the first times the derivative sine of y. Well, the derivative of sine of y, since it's just in terms of y, is 0, right? Because we're treating y like it's a constant number. Sine of a constant number is a number. Derivative of number is 0. Okay? Keep the first times the derivative of second, plus keep the second times the derivative of x, which is 1. So it's just 0 plus sine of y, which is just sine of y. So that is dz dx, or partial with respect to x of z. Okay. And dz dy, again, same thing. Keep the first, which is x, times the derivative of the second. Now, y is not a constant this time, so we actually differentiate sine of y like we normally would. So the derivative of sine is cosine, so we have cosine y, plus keep the second times the derivative of x. Well, the derivative of x, we're treating x like it's a constant because these are our partial derivatives. So the derivative of x is just 0 in this case. And so we just have x cosine y is dz dy. Okay. Now dx dt, we're taking the derivative of x with respect to t, so derivative of t squared is just 2t. And finally, the derivative of y with respect to t is just 2. Okay, the derivative of 2t plus 1 is just 2. So putting all this stuff together, we get that dz dt is equal to dz dx sine of y times dx dt, which is 2t, plus dz dy, x cosine y, times dy dt, which is 2. Okay? And what I want to do at this point is I want to substitute my values in for y and x, because the point of this was to find the change in z with respect to time. So we want to make sure our final variables are in terms of time, or t. So so we were given that x was t squared, and we were given that y was 2t plus 1. So let's go ahead and make these substitutions in here. Alright, so we have sine of y, so we have sine of 2t plus 1 times 2t plus x, which is t squared, cosine y, cosine 2t plus 1 times 2. And that is our answer there. You can simplify if you want to, but you know, it's fine to just leave it like that. Okay, so we want to find dz dt, the derivative of z with respect to time. When z is equal to xy squared, x is equal to e to the negative t, y equals sine of t. Okay, so first thing, I just look at everything that I have and see what derivatives I can find with respect to what. So with z, since z is in terms of x and y, I can find the derivative of z with respect to x, or the partial derivative, and I can find the derivative of z with respect to y. Alright, I can also look at x, and I can find the derivative of x with respect to time, so dx dt. And I can also find the derivative of y with respect to time. Okay? So putting all of this together, we have our formula dz dt is equal to dz dx dx dt plus dz dy times dy dt. Okay. Alright, so let's go ahead and find dz dx, so the derivative of z with respect to x, and we have to use the product rule here. So keep the first times the derivative of the second. Well, the derivative of y squared is 0, plus keep the second times the derivative of x, which is 1. So our answer here is just y squared. Okay. Sorry. Okay, there we go. Alright, so that was that. Now let's go ahead and compute dz dy, so partial of z with respect to y. So again, product rule, keep the first times the derivative of the second, plus keep the second times the derivative of the first. Again, we're keeping x as a constant, so that clears, and we're just left with 2xy. Okay, now if I find the derivative of x with respect to t, I'm using this right here, and so that's chain rule. I take the derivative of the outer function times the derivative of the inner function. So the derivative of e to the negative t, we just have e to the negative t times the derivative of negative t, which is negative 1. So it's just negative 1 e to the negative t. I don't have to write the 1 there. How about just negative? There we go. Alright, what about dy dt? So if I take the derivative of sine, it's just going to be cosine. of t. Okay, now putting all of this together, again, we're trying to find dz dt. So dz dt is going to be dz dx, it's dx dt, plus dz dy, dy dt. Okay, and now I need to substitute my x and y values because I'm trying to find the slope of z with respect to time, with respect to t. So y was given to be sine t, so I have sine squared t, it's negative e to the negative t, plus x is defined to be e to the negative t, so I have 2 times e to the negative t, and then another y, so that's sine of t times cosine of t. Okay, and that is my answer. That is dz dt, okay? Alright, let's try this one. So again, we're trying to find dz dt when z is equal to this, x is equal to this, y is equal to this. So the things that I can find, first of all, I can find the derivative of z with respect to x. I can find the derivative of z with respect to y. I can find the derivative of x with respect to t. I can find the derivative of y with respect to t. Okay, so let's do the z's first. So partial derivative with respect to x of z. So the sine, I have to use the chain rule here. So derivative sine is cosine. Then I multiply by the derivative of the inside. So the derivative of x over y. So that, I can use the product rule because x over y is equal to x, y to the negative 1. So I can use the product rule. So since we're looking at this with respect to x first. We're treating y like it's a constant. So when I multiply by the derivative of xy to the negative 1, I keep the first times the derivative of y to the negative 1, that's 0, plus keep the second y to the negative 1 times the derivative of x, which is 1. We're doing this with respect to x first. So this clears and we're just left with cosine of x over y times y to the negative 1. Okay, so that is that piece. Let's see. So we have cosine x, y to the negative 1. All right. Now let's do, with respect to y, let's do dz dy. So again, chain rule says I take the derivative of the outer function, multiply by the derivative of the inner function. So what's the derivative of xy to the negative 1 with respect to y? Well, I keep the first x, multiply by the derivative of y to the negative 1, which is negative 1 y to the negative 2, plus keep y to the negative 1, take the derivative of x, which is 0. Right, because we're doing this with respect to y. So all of my x's are constants. So this clears to 0, and I'm just left with negative x y to the negative 2. Okay? Alright, now the easy ones. So those were with respect to x and y of z. Now let's take the derivative of x with respect to t and the derivative of y with respect to t. So let's do this. Okay, so dx dt is just going to be 2, right? Take the derivative of 2t is just 2. So that's 2. And then the derivative of y with respect to t is just negative 2t. I'm just using the power rule up here. So now that I have all of these things, I can go ahead and use my formula that says that the derivative of z with respect to t is equal to dz dx, which is this, cosine xy, y to the negative 1, times dx dt times 2 plus dz dy, negative x y to the negative 2, times negative 2t. Okay, and now I can sub in my x's and y's to get my final answer in terms of t. So I have cosine of x is 2t over y is 1 minus t squared times y to the negative 1, so that's 1 minus t squared to the negative 1, all times 2, plus negative x, so it's negative 2t, times y to the negative 2 times negative 2t. And that is my final answer right here. All of this is dz dt. Okay, so if f, g, and h are differentiable, and if z is a function of x and y, with x a function of u and v, and y a function of u of v, then the following holds. So this is a little bit different from the first case, right? Because with the first case, we did have z depended on x and y, just like this. But remember, we only had x and y depending on t. Now this time, we're bumping it up, and we're saying, okay, well, x and y are going to depend on two variables, u and v, and that means that z is ultimately going to depend on two variables, right? If z depends on x and y both depend on u and v, then ultimately z depends on u and v, okay? And so we have this partial derivative formula. We say the partial derivative of z with respect to u is equal to this, okay? And the partial derivative of z with respect to v is equal to this. And we can kind of see what's happening here. You know, you can think about it like this if it helps you, right? We want dz du, okay? Or the partial derivative of z with respect to u. And so, you know, you can think of these as quote-unquote canceling to get dz du here, and these guys as quote-unquote canceling by getting dz du over here. So notice that we have the following. We have the partial of z with respect to x times the partial of x with respect to u. Okay, so these are like my x factors. Okay, and then we have the partial of z with respect to y times the partial of y with respect to u, so we can think of these as our y factors, right? Both of these involve a y, and they both involve a u as well. So we want x's and u's, and we want y's and u's, okay? Because we're trying to find the partial of z with respect to u. And in a similar way down here, if we're trying to find the partial of z with respect to v, these guys are my x factors, but this time with respect to v, we're dealing with v here instead of u. And these guys are my y factors. Okay, and again, we can informally think of these as quote-unquote canceling out to get the dz dv that we wanted. That helps me out to think about it like that, so you know, if it helps you remember it, fine, think about it like that. Let's actually do an example now. So we want to find the partial of z with respect to u, want to find the partial of z with respect to v, and so what I like to start by doing is to just list out all the things that I can potentially find with respect to partial derivatives. I'm given 3 equations here, right? And I can find a bunch of things. I can find 6 things in particular. So the first thing I can find in purple is I can find the derivative of z with respect to x. I can also write partial derivatives, that's what I mean there. I can also find the derivative of z with respect to y, so the partial derivative. In red, I can find the derivative of x with respect to u. Now, it was given, well, I guess it wasn't really explicitly given in this one, but what we want to assume here is we want to assume this situation. We want to assume that x is a function of u and v, and we want to assume that y is a function of u and v, okay? So we can find dx, du, and we should, in theory, be able to find dx, dv, since x is a function of u and v, okay? And same thing for the yellow. For the yellow, in theory, we should be able to find dy, du, since it's a function of u, but y is also going to be assumed to be a function of v, so we should be able to find dy, even though, the u isn't explicitly written there, we should be able to find dy, dv. And we're going to get some zero terms here, which is okay. So that's all the stuff that we need. Now, let's go ahead and figure out this stuff, and then we can figure out what this is and what this is. So first of all, derivative of z with respect to x. I have to use the product rule here. So keep the first times the derivative of the second, plus keep the second times the derivative of the first. So that's just e to the y. Okay. Now let's go ahead and do dz dy. Okay, so dz dy, keep the first times the derivative of the second, plus keep the second times the derivative of the first. So we just get x e to the y. Okay, now dx du, derivative of x with respect to u, while the derivative of ln of u is just 1 over u. Now what about with respect to v? Now there's no v's involved, right? So we can think of this as just 0. Dy du, again, for y, there's no u's involved, there's just a single v, so we can think of this as 0. And dy dv, the derivative of v with respect to y, the derivative of y with respect to v is 1, right? Derivative of 1v is just 1. So putting this all together, we have the partial of z with respect to u. Okay, so this is how I do it. I want to cancel things out so that I get that. So I have x dz dx times x with the u. That's here. Actually, maybe I'll just write it first so that you can see. Okay, so I see that cancels to get that. You see what I mean? Plus, and then I do the y's. So dz dy times dy, and I want it to involve u, so dy du. Okay, now I can plug everything in. So dz dx is e to the y, so I have e to the y times dx du, which is 1 over u, times 1 over u, plus dz dy, that's x e to the y, times dy du, which is just 0, right? Alright, so that clears to 0, and I'm just left with e to the y over u, and y, remember, we want this to be in terms of u's, right? So we want to get rid of the y. So the y was defined to be v, so we want it to be in terms of v's and u's, I should have said. So let's go ahead and sub in v for y, and we get e to the v over u. And that is my partial of z with respect to u. So we now want to find partial derivative of z with respect to v. Okay, so I have my x's that I'm going to write here, plus my y's that I'm going to write here. And first thing, I have dz dx. I want the dv on the bottom, so I'm going to multiply by dx dv, right? Because you can informally think of these canceling to give you what you want, which is dz dv. Okay, so those are my x's. Now my y's, same thing, dz dy times dy dv. Again, you can informally think of these dy's canceling there to give you what you wanted, dz dv, which was right there. Okay, so let's go ahead and just compute these. We already have all of these things from up here. So dz dx was e to the y. So we have e to the y times dx dv is 0 times 0 plus dz dy x e to the y times dy dv, which is 1. Okay. So that just goes to 0, and we're just left with x e to the y, and now I can plug in my x and y so that I'm just in terms of u's and v's. So my x was ln u, so we have ln of u times e to the y was defined to be v. So that is my answer, and again, that was the partial derivative of z with respect to v. Okay, so let's try this one. We have w is a function of x and y. W is x squared e to the y. X is 4u, and y is 3u squared minus 2v. So we want to compute the partial of w with respect to u, and then we want to compute the partial of w with respect to v. Okay, so let me go ahead and list out all of the things that I can find here that I'm going to need. So derivative of w with respect to x, or the partial derivative of w with respect to x. Then from w I can also find dw dy, partial of y, or partial of w with respect to y, I should say. From the yellow, we can find derivative of x with respect to u, dx du. And then we also have dx dv, because we're assuming that x is a function of u and v, even though v isn't explicitly written there. And finally, for y, we have derivative of y with respect to u, and the derivative of y with respect to v. So these are partial derivatives of y with respect to u and v. So let's go ahead and figure out what these are. So dw dx, we're fixing y as a constant, so we have to use the product rule here. Keep the first times the derivative of the second. Derivative of e to the y is 0 because we're thinking of y as a constant, plus keep e to the y times 2x. Okay, so we took the derivative of w with respect to x, leaving y as a constant. So we just have e to the y times 2x. Okay. Alright, now let's do dw dy. Again, same thing. Keep the first times the derivative of the second. This time we're leaving x fixed. We're finding the partial of w with respect to y. So x is a number. X is fixed. Keep the first times the derivative of the second, plus keep the second times the derivative of x squared. Well, that's 0. Remember, x is a constant number. So our answer here is just x squared e to the y. Okay, so in yellow, dx du, derivative of x with respect to u is simply 4. Derivative of x with respect to v is 0 because we don't even see a v. We don't see a v variable there. The derivative, partial derivative of y with respect to u is 6u, because v is being held constant. And the derivative of y with respect to v, so if we hold u constant, derivative of this guy is going to be -2. Okay, So using all of this, let's first compute the partial of w with respect to u. So for our x's, we have dw dx. And again, I know that the notation isn't perfect, but it's a way for you guys to intuitively remember why something goes where it does. So we have dw dx, so our x's along with the x that involves u. So this is dx du. And again, the reason I'm using the notation like this is because you can see that this kind of, it doesn't really cancel, but you can think of it as canceling to get the intuition that this is the partial derivative of w with respect to u, as we can see it there. Okay. All right. Plus, now the y's. Now we have dw dy, and then the y that involves u, so dy du. And now we can just plug everything in. So dw dx, so we have 2x e to the y times 4 plus x squared e to the y times 6u. Okay, so now I'll plug in for x, I'll plug in for u, and for y, 3u squared minus 2v. Okay. Alright, so now I can clean this up if I want to. I'm getting 32u e to the 3u squared minus 2v plus, let's see, this becomes 16u squared. So 16 times 6 is 96. So this becomes 96u cubed e to the 3u squared minus 2v. Okay, and that is my answer. That is the partial derivative of w with respect to u. Okay, well, let's do the other one. So now we have the partial of w with respect to v. Okay, so first my x's. So I have dz dx. I want x with v, so dx dv. Again, you can kind of see this cancellation right here to get this, which is what I like. Okay, and then plus the y's. So dz dy times a y that involves v, so dy dv. And then again, you can see the cancellation. Oops, that's not the right one. Right there to give us dz dv. Or sorry, this should not be z. This should be w. That is our dependent variable there. So anyway, you can see dw dv right there, and then you can see dw dv right here. Okay, that's how you know they're in the right spots. Okay, so the partial of w with respect to x, we found it. It's 2x e to the y. Partial of x with respect to v is 0. Plus partial of w with respect to y, x squared e to the y. And then finally, partial of y with respect to v is -2. And last thing I want to do is sub in my x's and y's in terms of u's and v's. So first of all, this clears to 0, so I don't even have to worry about that. So let's see, x squared, we have x was 4u, So we have 4u squared e to the, and then y was 3u squared minus 2v. Okay, times negative 2. And that is our answer. Okay, that is the partial derivative of w with respect to v.